This is the concept video for tangent planes, linearization, and differentiability. So, if you remember when you studied single variable calculus, you had graph of y equals f of x, the x and y axis, and at any point x0, I'll choose a better point than this, x0, we could have, there was a tangent line to the curve, f of x, and the slope of the tangent line was f prime of x0. And we only have a tangent line if f is differentiable at x0. So the equation for this tangent line, let's actually change this axis to z, because we're going to use z for heights now in multivariable calculus. So the equation for this tangent line would be z minus z0 equals f prime of x0 times x minus x0. And you can see this kind of makes sense. We have delta z on this side, if you want to look at it that way. And this is df, or dz, dx. And we have delta x here. So you can see these kind of cancel, and we kind of get delta z equals dz, so that's kind of why this works for very small changes from x0. Z0 is just f of x0 in this case, so you could also write this as z equals f prime of x0 times x minus x0 plus z0. And we called this the linear approximation for f at x0. And I'm gonna write this as f of x0 here. So we linearized our function at some point x0 by turning it into a line, essentially, and we use this to approximate values close. So if this was like 2, we could approximate f of I put 1 there. We could approximate f of 2.2, for example, and f of 2.2 is approximately L of 2.2, which is f prime of x0. So the x0's stay. That's just where your approximation is centered. And we know our x0 is 2, so that's how we'd approximate. So we have a linearization. Its geometric interpretation is the tangent line, and it only works if our function is differentiable. So now moving into multivariable functions. So let's say we have f of x, y. So now we have a surface, if you could recall. And we have z, the z-axis pointing up, and the y and x axes. And let's say we have some sort of surface above the xy plane. Its height at any point xy is given by the function f of xyz, or f of xy. Sorry. And Now, a line, if we go to any point here, one line isn't going to be tangent to the surface. We're going to have an infinite amount of lines all in different directions. So all these lines actually specify what's called a tangent plane. So, and the way that we can compute this plane, or the equation for the plane, so this will give you an idea of what the plane looks like. I hope. It's probably a bad drawing, but I'll see if I can draw a better one later. So let me just get rid of that. So what we're going to do is we're going to look at specifically two different tangent lines. And turns out we're going to look at the tangent line in the y direction, so that's this one. And then the tangent line in the x direction. That's that one, this one. And the slopes of these tangent lines, if you watch the partial derivatives video, and we're going to go at some point x0, y0. So this is or let me redraw that. Make this whole thing bigger. So we're above the plane, xy plane, at x0, y0. So this is x0, y0. And the slope at x0, y0 in the x direction was df of x0, y0 dx, partial derivative there, and then in the y direction we have df of x0, y0 dy, and these two will specify some sort of plane. I'll use a brighter color too. So our plane will look something like this. And I know it's kind of cluttered, but that's pretty much that's the gist of it. If you erase all these other extra lines, maybe you can see it better. Or not, I'll just draw another picture later. The point is, we have a tangent plane, and the equation of tangent plane, the tangent plane, is z minus z0, I'll move this here so we have room, equals df of x0, y0 dx times x minus x0 plus df dy at x0, y0, times y minus y0. And this is the equation. And z0 is just f of x0, y0. And this only exists if f is differentiable at x0, y0. And this is the linear approximation. If we solve for z here, we put z0 on this side, and I'm just going to write it as f of x0, y0, so we remember what it means. This is our linear approximation in terms of x and y in 2 dimensions, or 3 dimensions if you want to look at it that way. But the plane itself is a 2-dimensional object. So if you want to approximate something around x0, y0, you can approximate that as the linearization of f of x at x0, y0. So I think some examples will make that more clear. Last thing I want to cover in this video is differentiability. So I said the condition for this to work is that the function is differentiable. So there's a condition for differentiability. So f of xy is differentiable at x0, y0 if this limit here, the limit as xy approaches x0, y0 of the absolute value of f of xy minus L of xy, so the linearization, so the tangent plane equation, over square root of x squared minus x0 squared plus y minus y0 squared equals 0. So this is just, up here we have the difference between the actual function, so the surface, and the linearization, the tangent plane. So pretty much as we approach the point where the tangent plane should be tangent to f of xy, we should be approaching the same point, the same function value, so their difference should equal 0. And this is just the magnitude of the change in x and y. This is delta x squared plus delta y squared square root. This is just the magnitude and the change of, it's your position, so r, if you want to call it that, but that's unimportant. So yeah, this is also known as the error, and the error is vanishing. Another condition, another thing that works for this is also, so if this is true, the function is differentiable, but another easier way of doing this is f is, so I'll put or f is differentiable at x0, y0 if its partial derivatives, so f x and fy, sorry, I'm running low on battery, fx and fy are continuous at x0, y0. So if its partial derivatives are continuous, then your function is differentiable. And if these partial derivatives don't exist, your function is automatically not differentiable at that point. So yeah, that's all I want to say about tangent planes, linearization, and different. I'm in love with you.